Hello everyone, and welcome to my video on Maclaurin series. In my last video on the Maclaurin polynomial, that's where we actually start the process to ultimately come up with Maclaurin series. As I mentioned in that prior video, the goal of this unit is really to be able to come up with a power series for any function. And the idea of the Maclaurin polynomial was to basically the polynomial itself is almost like a partial sum to the power series, because the power series is an infinite sum of powers of x's, and a polynomial is just a finite number of terms. And I said that we developed that Maclaurin polynomial, and then with the idea that from that we can analyze patterns there to try to extend them to get the Maclaurin series, and thus a power series for any function. So that being said, if you recall from the last video, this problem here, we found the third degree Maclaurin polynomial for e to the x, and it was this here. And what I've essentially done is with the x squared term and the x cubed term was I just simplified them to just be one whole fraction of x squared over 2 factorial and x to the 3 over 3 factorial. Now, this was just a third degree Maclaurin polynomial, but if we were to perhaps start to extend this out, you might notice some patterns there, especially since every single derivative of e to the x is e to the x, and a value at 0 would just be 1. If you had to guess perhaps what the next degree term would be, especially pattern-wise here, because if you have x squared and x cubed over perhaps the same numbered factorials, if you had to guess what the next term would be here, if you guess x to the 4th over 4 factorial as the next term in this expansion of this polynomial, you would be right. And so here, if we continue to expand this out to higher powers of x's, essentially we would see that we would have, for every power of x, we would see the same number of factorial beneath it. In a similar fashion, last time we found the fourth degree Maclaurin polynomial for cosine of x, and after we simplified things down, this is what we were left with. But again, I just, perhaps especially with the x squared term and the x to the 4th term, kind of just rewrote them as one fraction. Now, in this fourth degree polynomial, we don't have every power of x, but if you actually happen to look at these powers, this is x squared, this is x to the 4th. Hopefully agree that one could be thought of as x to the 0. These are all even powers of x's, and they're all over the same numbered factorial. So if we perhaps wanted to extend this outwards, the next non-zero term here wouldn't be x to the 5th, especially from what we saw with our pattern-wise evaluations of the derivatives here. The next non-zero term here would be x to the 6th, and that would be over 6 factorial. And it would be a negative term because of the pattern we see here, because it's positive and negative, and then positive, and the next term would be negative. So cosine would have, if you expand this outwards, continue to expand this outwards, would just have even powers of x's over the same number factorial. Now, we didn't examine this problem here in the video, but I did put it in the formative. And the 5th degree Maclaurin polynomial, if you especially got rid of the 0 terms and you simplify things, this is what you would end up with. And here, again, we don't have every power of x, but this is x to the 1st, this is x to the 3rd, this is x to the 5th. These are all odd powers of x's, and they're over the same numbered factorial. And if you had to guess what the next non-zero term to these Maclaurin polynomials, if we continue to extend this outwards, if you guessed, well, it would perhaps have to be negative because of the patterns here. And if it was, you guessed negative x to the 7th over 7 factorial, you would be absolutely correct. So, with that being said, here are the Maclaurin series for e to the x, cosine x, sine x, and inverse tangent of x. And sorry to say, you will eventually want to have these memorized for your tests when you take it, because you're going to see in a moment that memorizing these and being able to apply these to find other Maclaurin series is going to be very beneficial to you. So how could you perhaps remember these? Well, years ago, a student of mine said, well, Mr. Ambrose, I remember E's Maclaurin series because in the expansion here, we see that we have essentially every power of x, x to the first, x to the second, x to the third, x to the fourth, and so on. So we have every power of x, and it's over the same numbered factorial. And as I just went over with cosine and sine especially, cosine, however, didn't have every power of x. It had all the even powers of x's over the same numbered factorial, whereas sine had all the odd powers of x's over the same numbered factorial. And to really drive this home about like memorizing or being able to especially memorize cosine Maclaurin series and sine's Maclaurin series, I'm going to remind you about something that you learned back in Algebra 2. And that was determining whether a function was even or odd. And one way to determine this back in Algebra 2 was to determine if there was any symmetry in the graphs. And the cosine function had symmetry about the y-axis, and as such, we said that the cosine function was even. But if you really look underneath the hood here, the real reason why cosine is especially an even function is because the Maclaurin series that represents cosine of x has all even powers of x's. And thus, and remember that this Maclaurin series is going to behave exactly like the cosine function around x equals 0. So cosine, since its Maclaurin series makeup has all even powers of x's over the same number, even number factorial, that's why especially cosine is even. Whereas sine, from back in Algebra 2, is odd because it was symmetric about the origin. But the underlying reason really why sine is an odd function is because its Maclaurin series makeup here is all odd powers of x's over the same odd number factorial. And you just have to remember that cosine and sine have alternation of signs here. Now, inverse tangent of x, its Maclaurin series, is the power series that we developed back in my video on differentiating and integrating power series. I said back then that you're going to want to have that memorized. And the nice thing is, I don't know if I remember if I said to memorize it, you're going to want to have it memorized. But the nice thing is, inverse tangent has, notice, has all the odd powers of x's here over the same odd number with no factorial. And what most students will do to remember the inverse tangent Maclaurin series is that it basically is the same as sine's Maclaurin series, but just no factorials. So again, you're going to want to ultimately, by the time of your test, have all these memorized. And now I'm going to show you especially why perhaps you want to have them memorized, especially to perhaps come up with other Maclaurin series. All right, so we're going to look at this example here. We're going to find the first four terms of the Maclaurin series for f of x equals e to the 2x. And I'm going to originally get these four terms by using the Maclaurin polynomial formula that I showed you in our last video. So that would mean that we're going to want to evaluate f of 0 as well as the first four terms would lead us to x to the third term. We're going to want to look at up to the third derivative of f, evaluate them at 0 as well to help us get the first four terms to this series. So f of 0 would just be e to the 0, which is equal to 1. Now to really keep track of things here, f prime of x, be careful, we have to do chain rule here, that would equal 2 e to the 2x. And that evaluated at 0 would be equal to 2e to the 0 or just 2. The second derivative of our function here would be, again, we have to apply chain rule, would be 4e to the 2x. So if we evaluate that at 0, hopefully you would agree that we get 4. And then the third derivative of our function would be 8e to the 2x. And that evaluated at 0, hopefully agree that that would be equal to 8. So now utilizing all these function values and derivatives, all valued at 0, using the Maclaurin polynomial formula, this should equal just 1 plus next term is x. Coefficient here would be 2, so it would be plus 2x. And then the next term would be the x squared term. And coefficient should be this f double prime of 0 of 4 over 2 factorial. And then after that, the next term would be the x cubed term, whose coefficient should be this f triple prime of 0 of 8 over 3 factorial. And there's a pattern here, and this would continue going on, but we just had to provide the first 4 terms of the Maclaurin series for this function. All right, so now what I'm going to do is I'm going to look at this particular setup here in a little more detail. And I'm going to have at my side here also the Maclaurin series for just e to the x. And the detail I want to look at here is I kind of just rewrote these terms. I put the 4x squared as the numerator and 8x cubed here as the numerator. And the idea that, or what I really want to try and get at here is that this was e to the 2x. And if you look at this 4x squared term, hopefully we would agree that, especially in terms of 2x, we can write 4x squared as 2x whole thing squared, and that's over 2 factorial. And again, I'm doing this because here this was e to the 2x, and there's the 2x being squared. And that's kind of tying into this term in our e to the x Maclaurin series. And if we look at the next term of 8x cubed, I claim we can also rewrite that in terms of this 2x. We can express that as 2x whole thing being cubed over 3 factorial. And so essentially what's happening here and what you can do, or we could have done instead of doing this whole long process here, to quickly come up with the Maclaurin series for e to the 2x like that, I claim what we could have done is taken the e to the x Maclaurin series. Since this is 2x, I claim we could have just taken that 2x and just plug it into each of these x values here, and we could have come up with the terms of this Maclaurin series very, very quickly and efficiently, a heck of a lot quicker than what I just did, right? Because plugging 2x into each of these here, we would get the 1, we would get 2x in for that x, we would get the 2x, right, being squared over 2 factorial, and then here we would plug in 2x and cube it and put that over 3 factorial. And like that, we could have come up with the first 4 terms in Maclaurin series for f of x equals e to the 2x. All right, so now I'm going to just do a couple more examples showing you how you can apply utilizing the formulas for our Maclaurin series to quickly answer questions. So this question here, it asks us to find the first 4 terms in Maclaurin series for f of x equals sine of x to the 4th. So I have here already written down the sine Maclaurin series, which again, it's all the odd powers of x's over the same number factorial. And here it is x to the 4th that is inside the sine function. So to quickly come up with the Maclaurin series for this sine of x to the 4th, I claim all we have to do is into the Maclaurin series that we have for sine of x, just substitute x to the 4th in for each of these x's, and we'll get our answer like that. So into the first term here, we plug in x to the 4th. We're just going to have x to the 4th. into the second term, the second non-zero term, I should say. That would be x to the fourth all cubed over 3 factorial. And then into the third term here, we would have x to the fourth, that whole thing to the fifth power over 5 factorial. And then minus, plug in x to the fourth into the fourth term here, we would have x to the fourth to the seventh power all over 7 factorial. And like that, voila, like that, we have our first 4 terms of the Maclaurin series for f of x equals sine of x to the fourth. And I claim that was a heck of a lot easier than using the Maclaurin polynomial formula, because if you think about it, we don't have to simplify these terms down. There's no calculus involved to do that. But if we did simplify down, especially this last term, the power that this x would be x to the 28th power, which would mean if you were to try and use that Maclaurin polynomial formula, guess what derivative you would have to go up to? You would have to go up to the 28th derivative of sine of x and sine of this function in particular to determine this coefficient. And you don't want to do that. That's why this is a heck of a lot quicker and a lot easier to find this Maclaurin series for sine of x to the fourth. All right, so for the next example, we're going to find the Maclaurin series for f of x equals to x squared, which isn't one of or related to any of the 4 functions that you have to have Maclaurin series memorized for. But I want to do this for a particular reason. So to do this, we're going to have to fall back on the Maclaurin polynomial formula. And in doing so, all right, f of 0 to this particular function is just equal to 0. The first derivative of this function is just equal to 2x, and so f prime of 0 would just be equal to 0, and the second derivative of our function would be equal to just 2. So then f double prime of 0 would be equal to 2, the constant 2. And the thing is, after the second derivative of this function, the third, fourth, and so on derivatives are all going to be 0. So what that means for our series, if we use our Maclaurin polynomial now to piece everything together, well, that would mean that x squared would be, okay, f of 0 is just 0. So, okay, nothing there really. The next term is the x term, whose coefficient would be f prime of 0, and that's just 0. The next term after that would be x squared, whose coefficient is f double prime of 0, and that we know is equal to 2, and put that over 2 factorial. But as I mentioned, from that point onwards, will be x to the third next, but all the derivatives after the second derivative, evaluate 0, it's going to be 0. So there's going to be really nothing else here. And this just simplifies down to x squared is equal to, or its polynomial and series here, it's going to equal just 2x squared over 2 factorial, and 2 factorial is just equal to 2. And that simplified down is just equal to x squared. And what you'll notice here is that the original function x squared, its Maclaurin series, is itself. And that's always going to be true for any singular particular power function x to the n. Claim that its power series is just going to be itself. And knowing that can help you come up with other Maclaurin series and other types of questions. Okay, so now we'll actually see where knowing that any power of n x to the n, Maclaurin series itself, will come into play. And that's with this example here. So here we're going to find the first 3 non-zero terms in the Maclaurin series for f of x equals x cubed times cosine of x to the 6th. And I claim to do this, what we can sort of do is we can come up with the Maclaurin series for x cubed and cosine x to the 6th separately, and then just multiply them together. And what you see here is I've already written down our Maclaurin series for just cosine of x. so that we especially can quickly come up with the Maclaurin series for cosine of x to the sixth. So with that being said, the Maclaurin series for cosine of x to the sixth would be, right, we're going to essentially, to do this, we're going to take x to the sixth, and we're just going to plug it in for each of the x's here in the Maclaurin series for cosine of x to quickly come up with this Maclaurin series. So this is just 1, so that would stay 1. But now into the second term here, we would plug in x to the sixth, and that would be squared over 2 factorial. And then into the third term here, again, we plug in x to the sixth, and that would need to be raised to the fourth power, and that's all over 4 factorial. And technically, that would be 3 non-zero terms, so we wouldn't need to really go any further here. And this here is the Maclaurin series for just cosine of x to the sixth. So now to get the Maclaurin series for cosine of x to the sixth times x to the third, we just have to multiply the two Maclaurin series for these functions, and we would have our answer. So x to the third, x to the third times cosine of x to the sixth, right? That would equal, well, Maclaurin series for x to the third is just itself, and then we would need to multiply that by this here. That would be 1 minus x to the, and I'm going to simplify this. X to the sixth to the second is the same as x to the 12th over 2 factorial. And then in the same manner, x to the sixth to the fourth is x to the 24th over 4 factorial. And voila, here is essentially our Maclaurin series for this function x to the third times cosine of x to the sixth. Now, I've always said that so long as there's no more calculus involved and you've answered the problem, you don't have to simplify things down. But I claim you have to simplify things down here in this problem because technically they want to see here really the first 3 non-zero terms. And technically those 3 terms is not explicitly seen there in the problem. And what I mean by that is we really need to distribute in x to the third so we can clearly see what is the exact first term and what is exactly the second term and so on. So the last thing we technically would have to do here is if we distribute this x cubed in, we would have x cubed minus, this would be x to the 15th over 2 factorial, and then we would have plus x to the 27th over 4 factorial. That there would be all we need to do to get our final answer here for the Maclaurin series for x to the third times cosine of x to the sixth. So thank you for watching my video. Hopefully this helped with learning exactly our Maclaurin series, why you want to have them memorized, and how you can apply them in a problem to quickly come up with other Maclaurin series. So as with the other videos and formatives, there is a formative for you to practice a couple of these problems, give those a shot, and when I return on Thursday, we'll kind of, go over everything and then proceed from there, see what other questions you have to do with the Maclaurin series. Have a great day, everyone.